Wasabi, you guys. Welcome to Integration Bee Training for Advanced. This is part 19.1, and we are about to learn Feynman technique. Okay, this is the integration bee trick that everyone has been waiting for. A lot of you guys has been waiting for this. And here we are. We are about to learn the Feynman technique. So let's get started with the concept. So what is this Feynman technique? So let's say a very great way to put it. Let's start with this integral, for example, because I think this is the easiest way to see the importance and the usage of why we use this. So let's say like we have like a function squared with an ln of this function. Oh yeah, I do want to say one thing about this technique of how I'm going to teach it. So the way I'm going to teach this technique, I liked the, how do I say it? The way we're going to sort of learn it is kind of the same way as like from India or like the Gmain notation, if that's what, I don't know how to describe it. The way we're going to do it is how it's taught in India, and the way we do is we use I of n. So this is what we call like, it's like an integral function, right? This is the same thing as like f of x, right? But we're going to label it as I of n for now. Okay? You'll see why. You'll see why. So this is a function. Okay? And I'm going to call it an integral function. Okay? Now, let's be honest. For any function that looks like this is disgusting. Okay? That is no bueno. It is horrid. So what we're going to do is we're going to turn this into an integral function. Now, the most difficult part about Feynman technique is that it's so like, there's so much freedom to wherever you want to place the variable, right? N could be placed here, n could be placed here, n could be placed wherever, right? That's the most difficult part, is like it's so free, but like what's the right way to do it, you know? And that's what I'm going to show you right now. So in this case, we're going to make an integral function out of it. And in this time, I'm going to place n to f of x. I'm going to place n right here. Okay? Now, let me show you why first. Why am I placing n there? Why not here? Why not x minus n, where n is equal to 0 or whatever, right? There's so much freestyle going on. Like when do we use it properly? So the reason why I put n here is because I can imagine, okay, well, f of x, remember this is an integral function, so everything else is treated as a function. Okay, so let me go like this. Okay, this is very hard to see because we're so used to x as a variable, not a constant. Okay, as you can see, I nearly messed up. This is n. Okay, or actually, I think it's better if I write it like this. It's a lot better if I write it like this. Okay, now just focusing on this, and I'm nearly, you see how difficult and confusing this could be? Okay, so deriving respect to n, okay, with respect to n, what is the derivative of this in terms of this function? Well, actually, there's no chain rule. I'm sorry, there's not in terms of this function, just in terms of n. Okay, so again, f of x, this is a constant. Okay, in fact, we could even call this a, if you want, right? It's like deriving dn a to the power of n, or whatever, if you want to, if that's easier for you to see. But the derivative of this is f of x n ln of f of x, because f of x is a constant. In this case, f of x is a constant. So that's what makes Feynman technique so powerful, yet so complicated to use, because it's hard to kind of juggle your mentality with it, because again, treating a function as a constant, like that's not normal. Okay, that's not normal to think. But in Feynman technique, that's literally what you're doing. You're treating functions as a constant. Okay, and that's what kind of mind boggles a lot of people. So here, right, if we want to get rid of this ln of f of x, we're going to derive it. We're deriving this. So in general, you're deriving this with respect to n just to cancel this out. Okay? So that's what we're doing. That's what we're doing. And this is one of the most common ways to use Feynman technique, is to the power. Okay? There are some times, I'll put this out. There are some times where we have like f of g of x, right? And we would put n here. Okay? Then with respect to n, we would do, f prime whatever n g of x. But then now g of x is here, right? Because it's a constant, right? And what that would help is, this would help integrals that would look like this, right? It would help with integrals that look like this, where you cancel out the g of x with this, okay? So just giving you some options. So those are like the only two like most common ways that we'll ever come across. The two most common ways. So in this case, we're going to use our first one. So this is our integral function. This is our integral function. Then we derive it and we call it I prime of n. So now this is I prime of n. This is our derivative. Okay. And now we derive this. This is now f of x n dx. As you can see, it is a lot nicer. And so now, because it's a lot nicer, and if it's like integrable, you can go ahead, integrate it, whatever. And then once you get your, whatever this is, in terms of n, fn, then you can go ahead and integrate it back, and you get your whatever function it is. Then you plug it in. In this case, what we have here, this is I of 2, right? Now, there is something I did miss, actually. Now I'm looking back at it. When you integrate, this is plus c. Okay? So when you integrate and you get plus c, you have to plug in, most of the time it's like 0, and then you just have to see whatever, assuming if f of 0 is equal to 0. But whatever this is, I should probably accurately write it this way. And then you solve for c, because there are some times where c does not equal to 0. So you have to be very, very careful with that. But most commonly, though, 90% of the time, c is going to equal to 0. Okay? So now that we got that out of the way, let's try implementing this in an actual integration bee problem. Alright, let's start with the famous one. Right? This is the famous integral. The integral that we keep seeing in YouTube videos. The Feynman technique. Okay? So, the reason why we have that minus 1 is because if that wasn't there, this whole integral would have diverged. So, with that minus 1 there, this integral does indeed converge. Okay. Next is a lot of the YouTube videos, they would just kind of go like this and be like, alright, let's let n equal 3, and they just dive into this and whatever. And it's like you lose track of like, wait, I forgot to integrate respect to n back. Or they'll even pull out the let's just use the double integral instead, and whatever, and Fubini's theorem, whatever. But I don't like any of those. I don't like any of those. Okay, it's too complicated. All right, when we're speed integrating, we don't want to make any big mistakes. So to prevent that, we're gonna do the India way, the G main way. We use I of n. So let's construct a integral function. All right. Well, because we've seen this so many times, we know exactly how to construct this. We're going to use our integral function to be x to the power of n minus 1 over ln of x. So now this is the integral function we created to see and try to make this integral a lot cleaner. So now that we've constructed our integral function, let's go ahead and derive it and see if it helps. If we derive this integral function, will our integral look nicer? And the answer is yes, because if you derive this with respect to n, right, x to the power of n, well, first of all, minus 1 over ln of x, that's a 0, so that's just going to be gone. So what we have left is xn over ln of x. If you derive x to the power of n with respect to n, you get xn ln of x. So the ln of x will cancel out, giving us x to the power of n dx. Okay? And we know this, right? This is power rule. This is equal to 1 over n plus 1. Okay, so our I prime of n, our derived integral function, is equal to 1 over n plus 1. Okay, so we have our derived integral that's equal to 1 over n plus 1. And now we integrate I of n is equal to ln of n plus 1 plus c. Okay, do not forget the plus c. Okay, even though the majority of the time c equals to 0, like we still want to make sure that, you know, this, whatever it is, we just want to make sure and double check that c is actually 0. Because again, sometimes it's not. And especially when you do like advanced integration bees, where it's challenging integrals, there are cases where they can even pull, and they could probably throw an evil integral at you and give you a case where c is not 0. Okay, you don't want that. So just to make sure, we'll add plus c in it. Okay, so how do we solve for c? Well, thankfully this is easy, right? If we let n equal to 0, right, it's going to be 1 minus 1, it's going to be 0. This whole thing is going to be 0. So if we let n equal to 0, we get I of 0. So we know that this is going to be 0, right? The integral is going to be 0 when we let n equal to 0. And then on this side, so if this side's 0, then this side's going to be what? ln of 1 is also 0 plus c. So c is equal to 0. Okay? Awesome. So we know that c is equal to 0. Cool. So let me go like this. So now we know that I of n is just equal to ln of n plus 1. And that's it. Okay, because we know c is equal to 0. So this is our integral function. This is our integral function in terms of the integral form. This is our integral function in elementary form or whatever. So now it's easier okay, we can just plug it in. Our original integral is n equals to 3. So I of 3 is equal to ln of 4, which is your answer. Okay, this is your I of 3. Okay, so in Feynman technique, you're literally just constructing an integral function and then deriving it to see if it's any easier. If it's not, you make another integral function and see if it's easier, and then you just keep on experimenting like that. Realistically, that's what you're gonna do. Okay, in this case, because this is so common, so famous, like we just know immediately how to do it. So because of that, I'll go ahead and give you more examples to make you more comfortable with this technique. Okay, so let's go ahead and do another demonstration of another integral example. Okay, so we have another tricky integral. Okay, this one's evil. I will say this integral is very, very evil. I'm not joking with you. This integral is very, very evil. Now let's go ahead. How do we construct an integral function for this? Well, I see that we could try n here. Okay, so let's try that. Let I of n equal from 0 to pi. And we're going to let ln of n minus cosine of x. Okay, so if I derive this, is it going to be easy? Well, let's check. All right, so the derivative of I of n is going to equal to, well, this is ln, so it's going to be n minus cosine of x, and this is just 1. Okay, it is not sine of x on top. It is not anything, whatever you think it is, okay? We are not deriving by x, we are deriving by n. Okay, we are deriving in terms of n, not by x. So sign of x should not be on top. Okay, it should look like this, no sign of x on top. Okay, just remember, like again, you know, it can be a little confusing. It takes a lot of practice and comfortability to use Feynman trick. Okay, we are treating, right now, we are just treating every function like it's a constant. Okay, now that we got that out of the way, so is this integral easy for us to integrate? It's not bad. I mean, yes and no. Realistically, but yes, in this case, yeah, we can definitely integrate this. It's just it would just be nasty because we have to use Weierstrass, and no one likes Weierstrass. So let's go ahead and use Weierstrass. So I'm just gonna color this for training sakes, right? So Weierstrass time, we are letting u equal tangent of x over 2. Okay, so now we have 0 to infinity, and then we have 2, 1 plus u square du. Then we have n minus 1 minus u square, 1 plus u square. Okay, so now we simplify this, we get 2 du. This is n plus nu square minus 1 plus u square. Okay, and now if we go ahead and kind of simplify this a lot nicer, we have u square of 1 plus n, and then we have plus n minus 1. Okay, so now this is, I'm going to go ahead and go like this. Divide, factor out 1 plus n. So I get u square plus n minus 1 over n plus 1. Okay? Does it look nicer? A little bit? Yeah. You see how where we can go off with this? Yeah? Yes, we can. So this is now 2n plus 1 times the square root of n plus 1 over n minus 1. Okay? And then with inverse tangent of u, whatever this is, it doesn't matter because when you plug in 0 or infinity, it's just going to equal to pi over 2. Right? We're just going to end up with pi over 2. So what we have is, let's see, this cancels out-ish, so we get square root here, and we're left with like n squared minus 1. Yeah, and then the 2 cancels out, so we should get pi over n squared minus 1. Alright, so we have I prime of n is equal to pi over the square root of n squared minus 1. Alright, cool. I know, right? This right here, using Weierstrass, it could be a little scary, but we just gotta just do it. You know, just breathe and just do it. Just do it, okay? Just do it. So now we're here, and look, we kind of persevered through it, and this is the beauty we get. Okay. So we have I prime of n equal to pi over square root of n squared minus 1. Okay, awesome. So now let's go ahead and we're gonna, well, this is the most annoying part. So when we integrate, like I said, we get I of n, and this is pi cosh. I'm sorry, inverse cosh. Pi inverse cosh plus c. Okay, the c, finding c is where it gets annoying, because I'm sorry to break it up to you guys, but that c is not equal to 0. Unfortunately, and I learned that the hard way. That c is not equal to 0. So how are we going to find this plus c? If you let n equal to 0, Okay, unfortunately, you cannot do that. We cannot let n equal to 0. That's gonna, negative cosine of x inside of a logarithm. You just can't. You can't. Okay, so what do? We have to test out other numbers. You just test out any n where this integral is just easy for you to compute. Unfortunately, the only easiest is letting n equal to 1. Okay, that's it. And this is where we have ln of 1 minus cosine of x. And then here we have to do some trig identities here. So 1 minus cosine of x, this is what? 2 sine square x over 2, right? So we would have like ln of 2 plus 2 ln of sine of x over 2. Okay. Thankfully, thank God that we can just memorize ln of sine of x, because like I said, this god dang evil integral appears way too often. It's evil. It is very evil. So, okay, so we have pi ln of 2, nice, plus 2, and then we have, let's see, if we do u equals x over 2, right, we get, okay, so we get 4 with pi over 2 ln of sine of x dx, right? So thankfully we know what this is. This is pi ln of 2 plus 4. Then the integral of this is simply negative pi over 2 ln of 2. Thank God we know it. Okay, this cancels out to be negative 2 pi. And so now we see that this is equal, so I of 1, this whole I of 1 is equal to negative pi ln of 2. All right, and now we have to solve for this side here. Pi inverse cosh of 1. What is inverse cosh of 1? What is that? Can you actually simplify that? You can turn this in terms of logarithms. So for those who don't know, inverse cosh, this is equal to ln of x plus the square root of x squared minus 1. How do I know this? Is because if you plug in cosh theta, you get sinh theta here, and then you get cosh theta plus sinh theta, which is equal to e theta, and then ln of e theta is just theta, in which you get back into inverse cosh. So that's how I know it's this. So pretty much it's the inverse of this. I mean, obviously, right? Because this is cosh, right? This is inverse cosh. So it's kind of like a quadratic formula to e to the x in a way. So, but I like to think of it as like a trig identity. Like, if it's inverse cosh, you plug in, make sure if you plug in cosh theta, it should work, right? If I had inverse sinh, right, then I would be like, okay, then I have to plug in sinh theta. Okay, so I know, let's see, sinh theta, because we're doing sinh theta, it must be x squared plus 1, because sinh theta here, sinh square plus 1 would become cosh, and that's where I know, okay, this is the correct formula for inverse sinh. Okay, so we're going to use inverse cosh in logarithm form because it's what we're familiar with. And so now if I plug in 1, we can easily see, inverse cosh of 1 is equal to 0. So in that case, what we have is that c is equal to negative pi ln of 2. Okay, so as you can see, this is one of the examples where c is not equal to 0. C is equal to negative pi ln of 2 in this case. So, okay, so now we know. So now if I delete this whole mess here, right? I can go ahead and delete this whole mess. And now we see that this here, c is equal to negative pi ln of 2. So now, what is our answer? So what we have is I of 2. So I of 2, this is equal to pi inverse cosh of 2 minus pi ln of 2. And if you want to simplify it, you can, right? This is ln of 2 plus what? The square root of 2 square minus 1. That's like root 3 minus pi ln of 2. It doesn't make it any prettier. It doesn't make it any prettier, but you know what? There you go. Okay? So this is our answer. Alright? So it's not just ln, it's not just pi cosh inverse of 2. Okay? It's also with minus pi ln of 2. This is your answer, your genuine answer. Okay? So be very, very careful for finding C. But again, things like this is rare. But if you're competing at like a very advanced integration bee, or like given like very hard integral problems, consider finding C first. Okay? But most of the time, it should just be C is mostly just equal to 0. Alright? Let's do another integral example. As you can see, we have secant x ln of 1 plus cosine of x. Alright. If I reform it like this, ln of 1 plus cosine of x, you can use integration by parts. Just good luck with that. But I think maybe Feynman trick might be a bit faster, or maybe somewhere that won't trap us in an ugly mess. So here now, because we have this, notice that okay, so we have cosine of x. It's a little sus. Maybe we can kind of cancel that somehow, maybe, right? But now let's say okay, well, let's say if this is an integration video about Feynman trick, maybe we have to consider making an integral function. In this case, I of n is equal to, well, maybe, let's say, let ln of n plus cosine of x, because 1's a constant, and most of the time we just use n as a constant, right? So, okay, so you try this. Let's say experimental reasons, like you don't know what's going on, but you just want to follow through if this is going to be helpful or not. So, okay. And then you derive this, right? And then you notice, oh, okay, this is just going to equal to cosine of x, n plus cosine of x. That's it, dx. Okay. So, do you want to integrate this? Because honestly, I don't. Okay. Partial fractions with cosine of x? I don't know. But I most certainly do not want to integrate this. Okay. So, so this integral isn't as easy as we thought. Okay, so we're going to retreat. What if we place n with cosine of x? So we're going to do 1 plus n times cosine of x. This makes a lot more sense. Why? Because when we derive with terms of n, this cosine of x is going to cancel out this cosine of x, right? Chain rule with respect to n, right? If we derive I of n from 0 to pi, right? Notice that we have cosine of x, okay, because that's just a constant, okay? Well, you know what I mean. But when we derive ln of 1 plus n times cosine of x, we get 1 plus n times cosine of x. But remember, right, because we have n here, you know, this is cosine of x, it's being treated as a constant, so we also derive n times cosine of x, which is cosine of x. Okay? And now they cancel out. And now this is a lot easier to integrate 1 plus n cosine of x. And yes, you are correct. We have no other choice but to use Weierstrass. So let's go ahead. Let's gather some balls and just persevere with Weierstrass. Okay, so let's go ahead. I'm just going to place that there. This is I of I prime n, just to label. And now we're going to go ahead and let u equal tangent of x over 2. Okay, so now this is from 0 to infinity, right? We get, I'm just going to burst straight through it because this is tedious. We get 1 plus u squared. You should end up like this, right? After using Weierstrass, plugging in everything. And then we want to separate it, which should give us 2 over 1 minus n. You should end up like this. You should end up, once you separated it and factor everything, you should end up in a case like this. U squared plus 1 plus n, 1 minus n. Okay? And then it's just like the same thing, right? This becomes, this is kind of opposite. Instead of n minus 1, it's 1 minus n. So it's similarly like the previous example that we did. So this should come out as pi over square root of 1 minus n squared. Aha! And we like this because this is super easy to integrate, right? So I of n is equal to pi inverse sine of n plus c. Okay, so now let's go ahead and find plus c. How do we find plus c? Oh, well, I mean, look at this. If we let n equal to 0, we get ln of 1. This whole thing becomes 0. So this is equal to 0. Nice. And we plug in 0 here. This is also equal to 0 plus c. Oh, c is equal to 0. Awesome. So this is gone. Nice. All right, now we just go straight in. All right, so now let's, what is our original integral? This original integral is equal to I of 1. So what we have is our answer is pi times inverse sine of 1, which means that the answer is equal to pi squared over 2. So this integral here is equal to pi squared over 2. Okay? And there you go. So this is realistically how you're going to be using Feynman technique. Okay, so it'll look like this. You'll experiment with your integral function, which way is easier, which n should I place to get an easier integral. And then sometimes you have to do Weierstrass substitution, so just burst through that. And then finding c, even though most of the time it's equal to 0, it shouldn't be too bad to check, right? So we'll just go ahead and check, see if c is equal to 0, you plug in n whatever, and then find c. And that should get to your answer. Okay? So this is realistically how the process would look like. Okay? Alright, another example for more practice. Another example. Alright, we have the inverse tangent of 2x over x squared plus 1. Now let me be honest with you. I would have never thought about using Feynman technique on this because it doesn't look like something that you would use Feynman technique, right? But I would not want to use, I don't know, Taylor series or integration by parts or whatever. But we're going to do Feynman technique. And the reason why I'm going to do it is because it's actually, to get rid of this x, but also, if you think about it, deriving inverse tangent of x is going to give you like x squared something plus 1. And then we have an x squared plus 1. Maybe we might do partial fractions. So let's go ahead, construct our I of n. I'm going to let this equal from 0 to infinity inverse tangent of nx all over x squared plus 1. Okay, and I like this because I'm thinking, oh, maybe that x is going to cancel out with this. And then this whole inverse tangent of n, whatever, it's going to become like x squared n squared plus 1. And we can do some partial fractions. All right, cool. I like that idea. So and you try it, right? You try deriving it, and then you end up with something like this. dx, and then you get, that x cancels out, right, when you derive it. So you should get something like n squared x squared plus 1, x squared plus 1. Okay? And then, look, this is actually nice. It's not bad. We can just do partial fractions. I mean, if we were given something like this, we would use trig substitution and do Queen's rule. But because we have a variable n here, we can't take that shortcut. But it's okay. That is okay. Instead, it's not too bad to just do partial fractions. Let's just burst through it. We'll just burst through it. Okay. Because they're both n squares, we can treat this like a linear function, so kind of like dummying, right? I'm gonna divide n squared, so we get 1 over n squared here, 1 over n squared here. Okay? And now what we have is, I'm gonna put the 1 over n squared here, and then what we have, that's a long line. I'm gonna go like this. Okay? So now we are separating it in terms of x squared plus 1 over n squared plus x squared plus 1 dx. Okay? Here, if we plug in negative 1 over n squared, we get, let me put 1 here. We get 1 minus 1 over n squared. Yeah. And then if we plug in negative 1 here, negative 1, we get 1 over n squared minus 1, right? Using the Heaviside method, right? You remember how to do this in beginner training. Okay. So now this is what we have. Awesome. You can actually go ahead and, if you want, multiply n squared. I think this is where we can just kind of bring it back technically. But when you do that, just for the sake of time, you actually get something. When you do all the algebra, you should get 1 over n squared minus 1 from 0 to infinity. And then you should be left off with, it should be possible for you to factor it out, technically. So you should be left off with x squared plus 1 over n squared minus 1 over x squared plus 1. Okay? And this is not bad. We get 1 over n squared minus 1. We get n, let's see, this would be n inverse tangent of nx minus inverse tangent of x, right? From 0 to infinity. And now what we have here is we have 1 over n squared minus 1. This becomes, what, pi over 2 n minus 1. Right, because if you plug in 0, everything's 0. Okay, and then n minus 1, you can actually cancel that out when you factor this. Oh, would you look at that? This is pi 2n plus 1. Okay, and this is our I prime of n. So what that means is our I of n is equal to pi over 2 ln of n plus 1 plus c. All right, how do we find c? Well, we have an I of n here. Oh, would you look at that? If I let n equal to 0, this whole thing is 0. So if n is equal to 0, this whole thing is 0. And n equal to 0, this whole thing is also equal to 0 plus c. Ah, c is equal to 0. Gotcha. So that means that c is equal to 0. Now my original integral is I of 2. And then you just plug in 2. Right? Our answer is pi over 2 ln of 3. A very nice answer. Okay, another great example of what it's going to look like realistically when using Feynman technique. Okay, so yeah, I know it's a lot to it's a lot of experience. Honestly, I'm not even experienced enough to commonly use Feynman technique, to be honest. So I'm with you, but this is exactly what it's going to look like. Okay? Alright, let's do one last easy, well, it's not exactly easy, but that's Feynman technique, right? But let's do a last example just for more practice. What's suspicious to you? We have cosine of x here and cosine of x here. So what do you think we should do? Feynman trick, right? We're going to cancel that out to make it look nicer. So let's construct an integral function, right? And call it from 0 to pi over 2. And we're going to place n inside here so that we can cancel out this cosine of x at the bottom. Okay, let's cancel out this bottom, get rid of this bottom here. So we have I of n, if we derive it, 0 to pi over 2. Okay, we get n square cosine square of x plus 1, right? And then times cosine of x, which would cancel it out. And then this, we should be left off with this, right? And as usual, I know, as usual, we would have to, well, actually, no. You actually don't have to use Weierstrass. No, we don't. You want to know why? Because what we can do is trig manipulation. As you can see, it's very important in our intermediate training that we do trig manipulation. Notice that we can multiply secant square top and bottom. And this would be n square plus secant square. So it'll be 1 plus tangent square. Aha! And now you can just let u equal tangent x. So now what we have here is from 0 to infinity, right? We have 0 to infinity of du n squared plus 1 plus u squared. Okay? And this is equal to 1 over the square root of 1 plus n squared, inverse tangent of u. Oh, well, I mean, we're plugging in 0 to infinity. So, I mean, no matter what, we're just going to get pi over 2 and then 1 plus n squared. Okay. And what is this? Easy. I of n, when we integrate that, this is simply pi over 2 inverse sinh of n plus c. How do we find c very quickly? Just take a look at this, right? N is equal to 0. So, I mean, we're letting n equal to 0 because it makes everything 0. So this whole thing is 0, plug in 0, this whole thing is 0. Would you look at that? C is equal to 0. So our original integral is I of 1, right? And so this is going to equal to pi over 2 inverse sinh of 1, which is like, what? ln of 1 plus square root of 2. So our answer is pi over 2 of ln of 1 plus square root of 2. And that is our answer. Okay? And there you go, you see? And notice how fast that was. If you were to do it with integration by parts, would it be easier? I think so. Now I think about it, maybe it would have been easier to use no, because this would be secant of x. So you would get what? ln of secant x plus tangent of x when you do integration by parts? Yeah. No, that's no bueno. Yeah, I'm sorry. But look how, I mean, we breezed through this, right? We just used the Feynman trick and we just solved it in like less than 5 minutes. I think that was less than 5 minutes. But realistically though, without me commentating and explaining it to you, right, you would have definitely solved this in less than 5 minutes, for sure. So, a very, very powerful technique, yet very advanced and hard to kind of mentally juggle with. So, it takes a lot of practice, it takes a lot of experience to get used to. Okay? Alright, and that is how to do the Feynman trick. Alright, so please, please, please get comfortable with that and practice redoing all these integrals by yourself on your own. And then, yeah, I hope that helps. Thank you so much for watching, and I'll see you guys in the next part.